Good morning, Algebra 2. Today we are going to do Algebra 2 Apex Semester 2, Chapter 3.6 and 3.7. So the first thing that we're going to talk about is how to evaluate natural log functions. So the natural log function is ln, or you can push the log button. So either one of these works. Ln just means that it is the inverse of 2.718. Log is for base 10. So for f of 3, we're going to come to our calculator here. And right here, you see the log button. And above, and here you see the ln button. So for the first one, it's ln of x. So I'm going to push ln. And you see it just shows that up there. And then I'm going to enter 3 and then hit enter. So my answer then is 1.09. Okay, so or 1.1, because 0.098, so it'd be 1.1. If you're rounding to 2 decimal places, which is what our notes say to do. So then I'm going to do log of x. So remember, whatever's in this parentheses is what you're plugging in for x. Okay, so I'm going to come down here. I'm going to hit my log button. Then I'm going to type in 24, enter, and I get 1.38. That's all we had to do on that one. Okay, so we're just plugging an x value in. Okay, so that you're seeing that log and ln actually correspond to a number. So let's take a look at the graphs of log functions. So this is an increasing log graph. So remember that for an exponential graph, an increasing or exponential growth looks like this. So when you take that and you do the reflection over the line y equals x, this is the log graph you get. And remember that these always go through. So for your parent function exponential, okay, which is y equals b to the x, it always goes through the point 0, 1. So a log function is always going to go through the point 1, 0. And the same thing for the decreasing. Okay? So we would take that over the line y equals x, and we would be able to then see that it always touches that same point, 1, 0. Okay, so some features of some log graphs. They're curved. It always increases if my base is greater than 1. It decreases if my b is between 0 and 1. The x-intercept is 1, 0, and the vertical asymptote is the y-axis. So when we were looking at our exponential functions, it was the x-axis. Now that's reversed, or it's reflected, so now it's the y-axis. Because remember, when you reflect something over the line y equals x, your x and y values swap places. My domain is going to be x is greater than 0, and my range then would be all real numbers. Okay, so you see it actually goes past the x-axis, okay, but it does not go past that y-axis. Okay, once again, we can move these and transform them, and that's what these talk about here. So transformations of log functions. So this is the exact same thing as we've seen this whole time. So anything on the outside is vertical and the same. And anything on the inside is horizontal and opposite of what it looks. Okay? So taking a look at this one, this negative means we reflect over the x-axis. This 3 is a vertical stretch of 3. Vertical stretch of 3. Okay, and out here it means that we move down 4. So this whole graph is shifting down 4. Okay, there's nothing with the x here, so nothing is changing in that spot. Okay, so it's not moving horizontally at all. Okay. Let's go ahead and take a look at a real world problem that you might see. So this is the earthquake problem. So we know quite a bit about earthquakes. And we use the Richter scale. Well, the Richter scale was only meant to for earthquakes in California, but we now use it everywhere. So here is a formula. The equation R of x equals 0.67 log 0.37x plus 1.46, where R of x is the magnitude of the earthquake on the Richter scale, and x is the energy of the earthquake in kilowatt hours. So one thing that I forgot to add to this note guide is that an earthquake measuring 2 on the Richter scale has 17.3 kilowatt hours of energy. So we want to know approximately how many more kilowatt hours of energy does an earthquake measuring 3 on the Richter scale have than one measuring 2. So the very first thing that we are going to do is we are going to graph our function. Okay, so I'm just going to graph this function here. So 0.67 times log 0.37x, close my parenthesis, that's important because otherwise it'll take the log of everything after that, plus 1.46. I can do a couple of things. One thing I like to do is always graph if there's a line like this. So that would be my y value would be 3. I could graph that in R2 and then I could see where they intersect. So if we type 3 there, okay, and then we touch graph. So you see it's way over here. So I'm going to zoom out just a little bit in hopes that we can see it better. We can see where it intersects. Okay, so that really did not make things very pretty. So we have a couple of options here. What I would do is I would do second calculate, okay, and I'm going to come down here to intersect. So you guys have done minimums and maximums and zeros. So now we're going to do intersect. Okay, so now I'm just going to choose my first curve. Yep, there it is. And then I'm going to hit enter. Okay. And then enter, maybe. There we go. And then I'm going to choose my second curve, and I want to be somewhere on my second curve here. So I'm going to hit enter. Okay, and then it says, hey, do you want me to guess where this intersects? Hit enter again. And that's going to give us a point. I think I must have hit something wrong while I was explaining this. So second calculate. We're going to where these intersect. So there's my first curve, there's my second curve. Guess. And I have something in here wrong. So let's go to my error. 0.37x plus 1.46. Okay, well, I'm not sure why it is not giving me an answer here. It should be giving me an answer. So what I'm going to do, since it's not giving me an answer, that's not an issue. I'm going to go ahead and I'm just going to go to my table. Okay, so when I'm here in my table, I'm looking for a y value that equals 3. You can see that I'm already pretty close to it, but you want to make sure that you find where y actually equals 3 here. Okay, so it's pretty close to 540. It's between 540 and 535. Okay, so the reason I wanted you guys to try it the other way is because this would take a long time to get to. But if you notice that your values are increasing or decreasing very slowly, then go into your table. So I would go into second and table, okay, and I would start, you know, probably at 0, and I would go by like, I don't know, 20s. Okay, so then when you go into your table, it's going to be increasing a whole lot faster there. So you're going to hit that 3 a whole lot quicker than if you were just doing it individually. So we know that it's between close to 540. So, you know, we can say 540, okay, 3 is our answer there. So now we're going to take the x closest to that point, and we're going to find the value of that x minus 17.3. So 540 minus 17.3, and we're going to get approximately 522.7. So on the Richter scale, an earthquake measuring 3 has approximately 522.7 kilowatt hours more energy than this scale of 2. Actually, we just had like a 5.9 earlier today. You know, I think about how much that shook and how much, you know, these other, the one in 2018 shook, and definitely you can notice a difference. Anyways, just an aside. Okay, so let's go ahead and move on to 3.7. So we're going to talk about properties of logarithms. So logarithms are very similar to exponents. Okay? Anytime with exponents, when we were multiplying exponents, we always added the exponents. So if we were multiplying a base, then we could add the exponents. Same thing here. If we're multiplying, we can change it to addition. Division, just like with exponents, changes to subtraction. Okay, now keep in mind that these have to have the same base, okay, especially if we're going from this way back to combining it, simplifying it. Okay. This is the argument raised to a power. So anytime you have that, the exponent always goes to the front. Okay, so you can see here that that exponent has moved to the front. So inverse properties. So this is just where we rewrote it as an exponential function. This one right here shows that if you have log base b and you have b as the argument, those cancel and you're left with just that value. And the same here. So the argument b raised to the power of log base b just leaves you with whatever that exponent is. Okay. So let's take a look at how we're actually going to use some of these. We're going to be solving equations and stuff eventually. Well, actually here shortly. Well, I guess it's going to be one more day before we do that. So let's go on ahead and we're going to simplify and change these up. So this one says write each expression as a single logarithm. First thing I need to check, are the bases the same? Yes, they are. So the bases are the same and it's a plus sign, which means it's going to be multiplication. So I'm going to have my log base 4 and then I'm going to multiply 2 times 32. And when I finish simplifying that, 2 times 32 is 64. So it's log base 4, 64. That's my final answer. I'm just simplifying this. I could solve this, but I haven't taught you guys how yet. So right now we're just simplifying. Okay, so for number 2, the base is the same and it's subtraction, which means division. So I'm going to have log base 5 of 625 all over 25, which leaves me with log base 5 of 25. You can simplify that more once again, but we're not going to do that right this second. And how could you simplify that more? Well, you'd set it equal to x, right? Change it to an exponential function. So you would have 4 to the x equals 64. And so then you could go ahead and simplify that down, okay? Or solve it even. But like I said, right now, I just want you guys to combine like terms. So this one right here, we're going to simplify. So you see we have 81 squared. Okay, well, this squared needs to move to the front. So that becomes 2 log 3, 81. Well, let's see if we can get anything to cancel. So 81. Can we raise 3? So we want it to have the same base and argument. So we need to see, can we raise 3 to some power and get 81? Yes, we can. 3 to the 4th power is 81. Okay. So now I'm left with 2 log base 3, 3 to the 4th. Well, this and this cancel. Okay. And then I'm going to be left with just 2 times 4, which is 8. Okay, so this 2 is down here. Now this 4 is down here. So now it becomes 2 times 4. Okay. And if you had left it up here too, it would have been log 3, 3 to the 4th. And then that raised to the 2nd power because that whole 81 was raised to the 2nd power. So it would have been 4 times 2 and still 8. But it's easier usually just to move that exponent to the front first. So let's do the same thing with this one. So we're going to move this to the front. Okay. So that's going to become 3 log base 5. Okay, well, this is a subtraction problem. Okay, so we can either do it as a subtraction or we can leave it in a fraction form. So if I change this and just leave it as 1/5, I can find out what I have to raise this to the power to. That way these two things will cancel. Okay, so this would have to be 5 to the first power to give me 5. Okay, and I can do that by saying, okay, well, 5 to the x power equals 1/5. So that gives me 5 to the negative x, right, equals 5, because I had to flip that, find the reciprocal, or I could have found the reciprocal there. Okay, and so we know that x then has to equal -1. So now I have 3 log 5, 5 to the -1 power. Those are going to cancel, and I'm left with 3 times -1, which is -3. All right, let's go ahead and simplify these ones. So we're going to be doing the same thing. So log base 8 and the 8 cancel, and I'm left with 3x plus 1. Log base 5 of 125. Well, we need them to both have a base of 5. So we need it to be log base 5 and then 5 to some power. And we know that 5 to the third power gives us 125. So now we can cancel those, and we're left with just 3. This one right here, the 2 and the log 2 just cancel. So remember, logs and exponents are opposite. Okay. So remember, in our equation where we write y equals, let's see, x. Let's see, I'm trying to figure out the best way to write this for you guys. So if I write it as x equals log by, so x equals log by, okay? So if these two things are the same, okay, then it's just going to cancel to equal that, okay? And vice versa when we have exponential functions, okay? So let's continue canceling. So log base 3 and the 3 cancel, and I'm left with 11. Okay, well, this one is log base 3, so I need something. I need a 3 to some power to get 81. Okay. And I know that that is 3 to the 4th power, so those are going to cancel, and I'm left with 4. Okay. And then my 5 and my log base 5 cancel, and I'm left with 10. Last thing we're going to do today is the change of base formula. So anytime we have a common log or the natural log, we're not going to have to change the base. So if we have log base 10 or ln of x, then we're fine. But a lot of times you see that we have log base 3, log base 8, log base 5, and we need to be able to calculate a value. So our change of base formula just says that we're going to distribute this log essentially. So it's going to become log of this divided by log of the base. Okay. And some of your calculators will actually do this for you, but it's really handy to know the formula. So then on my calculator, I'm just going to do log of 7, close that parenthesis, important, divided by log of 3. Okay, and I get 1.77. So I actually get a value for this. So let's try this next one. So I'm going to take log of the argument. So log 1, 2, 3, okay, divided by log of my base. So when I punch this into my calculator, make sure you close that parenthesis, divided by log of 5, I get 2.99. And then this last one is log base 2e. Okay, so I'm going to have log e over log 2. So distribute that to both of those. Okay, so log e, and it's e to the first power because it's just e. And make sure you close both of those parentheses, divided by log base 2. And you should get 0.217, but somehow that didn't happen for me. So let me see what happened here. Log E, that's to the first power, equals divided by log of 2 equals, and oh, so yeah, 1.44. Okay, so go on ahead, make sure that you know how to do this. Make sure that you can plug these into your calculator. You're going to have some practice on this today, and you guys have a great day.